Thanks. And it's really nice to hear from David Bromwich, who was a good inspiration for my work. I have two presentations. The first, precipitation extremes around Greenland, and the second is about dealing with 30 years of high resolution data and some comparisons with ERA 5. Thanks for being here. And what I'm presenting is based on an article we published this July, Greenland Ice Sheet Rainfall Climatology Extremes and Atmospheric River Rapids. I'll get into this idea of rapids in the following, and I'll add some detail what is not in this rather long study to keep it interesting. The story began when I convinced colleagues at the Geological Survey of Denmark and Greenland to put simple tipping bucket rain gauges on these climate recorder stations. And we can be confident about their accuracy when winds are low and temperatures are high, so we know we're capturing rainfall. That's what we focus on. And also when the rainfall intensity is high. Lots of details in the study about how we manage errors, which are well known for precipitation, undercatch, etc. You can see there's just a couple of regions that we used, that we started recording rainfall in 2016. And looking at the data, a very large rain event grabbed the attention that this study focuses on. 200 millimeters. These flooding events that we've been hearing about in the news, they're about 100, 200 millimeters. So this was a kind of a flooding event on the southern Greenland ice sheet. And the rainfall map for that date, according to CARRA, has near the southern tip of Greenland, you see these yellow colors, that's over 260 millimeters of rainfall. And luckily enough, that's where our observations were. You see plenty of detail here, like offshore intensification of rainfall and a tip jet structure that I'll add some detail to. The winds, very strong onshore flow, above 30 meters per second, delivering huge amounts of not only moisture, but heat at a time of year, okay, September 14th, it's like, you know, the end of summer stormy conditions that are returning to the North Atlantic. This is ERA 5 data on the left. The yellow colors are precipitable water. So you could argue it's an atmospheric river. And then on the right, you'll see the red colors. These are temperatures above melting, well onto the southern Greenland ice sheet. So strong onshore flow, lots of heat and moisture. It's a kind of a funny circulation with, you know, low to the southwest and a high to the southeast. These are vertical velocities over time, and the red colors are updrafts. And besides the very strong up and downdrafts in the Greenland fjords, you'll notice around the middle of the map, you have this relatively gently sloping part of the southern ice sheet that has terrain that focuses the flow onto the ice sheet. And at a certain few moments in this animation, you'll see it's mostly red color. So there was a large scale uplift over this part of the ice sheet. Some wind speed streamlines. There was a really strong flow disturbance around southern Greenland, a splitting of the flow, channeling of the flow here at 1000 HPA near sea level. And here we get a kind of a scan upward into the atmosphere. You see vertical velocities in the background of the red blue colors. And you'll notice as you go up to say 850 HPA, notice that strong red color on the southern ice sheet. This is a large uplift area that the CARRA data resolves in spectacular resolution. The rainfall not only was there rainfall focused on that southern part of the ice sheet, but uh, bands of rainfall appeared along flow. And we started to call these, struggling for a name for them, updraft filaments. That's what you see in the red contour lines is a long flow, strong updraft. And just below that in the blue colors, you'll see enhanced rainfall. So all the way along flow, downstream of this offshore updraft jet, you'll see the updraft arc going around this disturbance and the continuous precipitation along what we eventually called rapids. And I think I've already shown this. The observation sites are the yellow stars and that southern part of the ice sheet, the Casimir lobe. And in the following, I'm going to show the CARRA data in the vertical dimension along that dashed line to understand what was happening aloft. And so the pink line on the map to the right is what you're looking at from south to north. So on the left side of the graphic, you have you're scanning north onto the Greenland ice sheet. There we have the vertical dimension in the CARRA data. So this is the north-south component of the winds. The red colors and the oranges show strong northward flow. The zonal component, the blue colors near the surface, show flow to the west and perhaps a kind of return flow aloft up at, say, 10 kilometers above ground. Relative humidity, supersaturation in orange, and so the whole kind of troposphere was very moist, of course, as part of this atmospheric river. The dry patch next to the ice sheet down low, that's from local shelter effects. What you see in the zonal winds back here, it's actually calm winds down in that sheltered area. And there could also be some, because of the westward flow, a kind of a dry effect, a föhn effect, if you can see my mouse as the flow goes from east to west. So lots of local detail. The cloud snow water content, you can see kind of the snow line above about 3 kilometers altitude. There was snow water up to 8 kilometers above ground. So a very moist atmosphere. It's say snowing aloft, or snow is being produced, and below that snow line, rainfall, and a blending of less and less rain above that snow line. So some mixed rain and snow at about 3 kilometers. Rainwater content, you see it maximum over the ice sheet. And the vertical winds, you have to look in detail, but the coastal terrain is kicking off gravity waves up, enhancing the updrafts right where my mouse is. But then upstream of that, and here's the offshore updraft jet, it produced strong vertical velocities for several kilometers in height. And that was maintained in this area along flow in what we ended up calling an atmospheric river rapid. This was a detailed structure within the atmospheric river that we're not sure it's even real. But when we're looking at this very fine resolution, not sure if it's real, we would need some kind of aircraft measurements to confirm that there are these along flow kind of curtains of updraft. And then on reaching the Greenland terrain, there's an enhancement of the vertical winds. But as you'll see soon, it's not just the terrain forced uplift. There's a buoyancy component that it's already obvious here. And so I first started looking at isentropic surfaces because you may know about gravity waves, and people use these dry isentropes. But of course, with all of this moisture, it's not that realistic to use dry isentropes. So with pseudo-adiabatic moist, what I call moist isentropes, those are the thicker gray lines, and the atmosphere wants to flow parallel to these. The moist isentropes are a hypothetical quantity that assumes the moisture drops out instantly. So they're really most useful to track the direction that the atmosphere would like to flow according to buoyancy alone. And so this clearly indicates strong buoyancy, even vertically extended moist isentropes. So very strong buoyancy effects that combine with the terrain forced uplift to ultimately enhance precipitation. Yeah, I think I just included this to illustrate, yeah, the effect of the updrafts and buoyancy on the generation of, well, snow above 3 kilometers. We saw this rain below, and just a few more slides. I compared the field data with a number of regional climate models, starting with ERA5 at 31 kilometers grid spacing. This weighted average is weighted by the number of rain observations. These were daily rainfall rates. And then the average, or the sum of observations divided by the sum of the model, indicates that the observations were wetter than ERA5 by about 40%. A Japanese model, a little bit closer to the field data. The field data are completely independent of these data sets, by the way, so they are not assimilated. MAR, a Belgian model, getting closer to the field data. RACMO, a Dutch model, getting closer, and the correlations tend to be higher. And the CARRA data at its fine resolution had the highest correlation, and on average matched the observations. This was very encouraging, of course, and perhaps not that surprising. After all, CARRA is assimilating a lot more information into the domain and benefits from the high resolution. If you're familiar with precipitation studies, you know that it's very challenging for models to place precipitation accurately, and certainly we would like to do more verification work, but this again is very encouraging. So here's a look at the daily rainfall on this extreme event, and in ERA5. And so I'll compare the two. We can go back and forth between these slides, but the difference map really tells the story that we've seen in other examples, what has been referred to as a spillover effect. You'll notice the green areas are where the ERA5 is greater than CARRA. And you'll notice near the coast, ERA5 is drier than CARRA. And this is very likely due to the fact that at 31 kilometers resolution, the terrain is being smoothed out for ERA5. And so it cannot produce such sharp local orographic precipitation as what you can get at a finer resolution. And so the moisture drifts further inland before falling out. So we see this pattern of much more focused rainfall and even snowfall due to simply the higher terrain resolution, the spillover effect. So ERA5 does a good job in placing the weather systems in generally the right place, but in placing extreme precipitation, it's a good idea to go to finer horizontal resolution. And the final slide I have is 31 years of rainfall change. And the blue colors indicate it's raining more on the Greenland ice sheet, practically everywhere. This area down here is not statistically significant, and it's just a testament to the high interannual variability, really, why a trend didn't come out of the data there. But elsewhere, the pattern is uniformly of increasing rainfall by more 30% more rainfall over this 31-year period. It sounds like a large increase, 8 gigatons. It's a large number, but it's pretty small compared to the snowfall, which is more than 800 gigatons. But you get a large number because it wasn't raining much in the past, and now it's raining more at a time of year when it should be snowing, kind of thing, like September. That's it for these slides. I've got another presentation after this, but I'd be happy for any discussion. Thanks for your attention.
Thank you, Jason. I don't know if you have any questions right away now, but Jason, you're also going to give the next presentation about adaptation of the ERA 5 climate trends to CARRA data. So if there are no questions right now, I think we'll just continue, and then please post the questions in the chat, and we can take it all after Jason's second presentation.
All right, and thanks again, everyone, for being here. I'll talk about some of the challenges of working with 30 years of heavy data and some of the results that we get in comparison with the ERA 5 data that we know and love. And so I went ahead and posted a YouTube video on how to gather the CARRA data from the Climate Data Store. And we already heard this morning a really nice presentation on the same topic. Let's see. The other point on gathering data is that, yes, indeed, 31 years of 2.5 kilometer data, it takes time. The good news is that the Climate Data Store is retrieving the data a lot faster than they were a year or two ago. And so don't believe all the rumors that it takes too long to gather these data. And yeah, you have to be patient. It's heavy data. And I was happy to hear earlier a question asking for a regional subsetting of the data. That will be even more relevant for CARRA 2, which I think not all the users will want the full Arctic domain or a lot of the Northern Hemisphere at that resolution. So it seems a strong need for regional subsetting. I'll talk about resampling ERA 5 to CARRA data to make a difference map. And I've already posted data here. I should push it again, actually, to I think I'll just do that now for fun here. I just have to go like this, so that if anyone's grabbing the data now, there it is. It's pushing the latest version up to GitHub. Okay, great. That seemed to work. And then I go back for my presentation. So there's a lot in this code about not only resampling ERA 5 to CARRA, but handling the data. There's also in the same repository the gather data script that I talk about in this video. And I intend to make a video describing this process. It's just a few codes, but the codes get kind of long. And we heard an earlier presentation today. We did fewer lines of code. But I think this is still quite useful to get you into working with the CARRA data. So I'll compare some ERA 5 versus CARRA for both 2-meter temperature and total precipitation. And this is for this west domain of CARRA. So already here you see ERA 5, June, July, August for a 31-year period that is resampled to the CARRA grid. I use nearest neighbor so you can see the kind of Lego effect if you squint your eyes here. And we can see this circle is at the minimum. So the minimum temperature for ERA 5 is minus 14 Celsius at this latitude, longitude, and the maximum is down here. Here's the same thing for the CARRA data. Overall minimum in summer, minus 16. The zero, the max is down here. I'll just flip back and forth between these and look at like North Greenland. I think that's the most obvious difference between these data sets, where ERA 5 is colder in North Greenland in summertime. But to really get it, to appreciate the difference, here's the difference map made using the code at that repository. And I just make some notes that, well, these data sets are in general agreement over the North Atlantic. And in summer, the Southern Greenland ice sheet, ERA 5 and CARRA are in agreement. And along the Greenland ice sheet margin, see the white colors, that's where difference is zero. So there's a strong boundary effect between land and ice sheet, but it seems to be to our benefit if you're using ERA 5 to get an accurate number right at the ice margin. However, warm differences over northern Greenland, Iceland, Svalbard, and this part of the Arctic Ocean, etc. It's difficult to see, but you can actually make out the Northeast Greenland ice stream, and that's a testament to the very fine resolution of the terrain data used in CARRA. And yeah, you'll see some strong differences in fjords, where of course at 31 kilometers, ERA 5 cannot resolve these large amplitude terrain variations. Here's at the annual scale, and there's widespread warm difference for ERA 5. So ERA 5 is warmer over the entire ice sheet at the annual scale. There's a warm spot over Kane Basin, Nair Strait that David Bromwich was talking about. It's a very, very interesting region biologically, culturally. Lots of studies focus here in atmospheric dynamics. So that's an interesting difference. But again, ERA 5 warmer over Iceland, Svalbard, and say Baffin Bay. The winter months, it's just a stronger average difference, above 4 Celsius for most of the Greenland ice sheet, and then a cold difference. ERA 5 is colder than CARRA over land. I'll talk about, I have in situ data to compare these to get an idea of the absolute accuracy of both ERA 5 and CARRA. But then these are the averages, right? Here's a cruder map of the trend in ERA 5. So ERA 5 has a warming trend over Baffin Bay, warming trend over Svalbard. At the annual scale, a cooling trend, a very weak one over central Greenland, no trend here, and a cooling trend over the North Atlantic. CARRA has really only a warming trend, or not any trend here in the southern North Atlantic. So go back to ERA 5, a cooling trend, if I did the trend calculation correctly, and kind of no trend here for CARRA. The strongest trend around Svalbard and Kane Basin, not Kane Basin, the CARRA Sea, Laptev Sea, sorry, CARRA Sea, Barents Sea, that's it. The difference in the trend, the blue colors suggest that the CARRA trend is more positive everywhere. And so a stronger warming trend in CARRA over around Svalbard and the Barents Sea, is a consistent result with Isaacsen and others recently, where here is the CARRA trend. It's stronger than the ERA5 trend. Now to the in situ data, I'll emphasize the longest records we have from Summit and Swisscamp as part of our network that have now merged. The PROMISE network down low, the red sites merged with the blue sites, the Greenland Climate Network, carried forward by the Geological Survey of Denmark, Greenland, where I work now. I've compiled the Swisscamp data. We have 33 years of continuous measurements. You see summertime warming of 1.3 Celsius, an annual warming of 2.4 Celsius. That's by combining these in situ records. Similarly, at Summit, it was the University of Wisconsin that kicked off the Summit temperature measurements in May of 1987. And through 1994, there was some overlap. There should be some overlap here, 96, 97. And here we have 36, actually now 37 years of temperature data and other climate data from Summit. So how do these compare with CARRA and ERA5? Swisscamp at the annual scale, in situ is the black curve. It is very encouraging to see the strong variability is captured in all of these data sets. And the truth is that CARRA is assimilating the in situ data, not all of it, but most of it. And here you see that warm difference that we saw for ERA5 versus CARRA. And down here, some statistics. So CARRA has an average bias, which is just above 1 sigma, and the bias at ERA5 is well above 1 sigma, and a slightly higher correlation for CARRA at the annual scale at Swisscamp. Winter, and this is where the temperature differences are largest. They dominate the annual signal. ERA5, quite a bit warmer. The difference is 5 Celsius for this location in winter. I start to wonder if some of this is a terrain smoothing effect. The near margin terrain should be smoothed lower at 31 kilometers. So some of this warm bias is probably due to that, but that would not explain what we see at Summit, where there's little terrain bias. But here we have a nice agreement with the CARRA data. High correlation, it's about as high as for ERA5. And let's look at summer. So in summer, CARRA is slightly less or slightly larger bias than ERA5. And you saw in the earlier maps that the southern ice sheet has a small difference with ERA5 and CARRA. And here it seems that ERA5 is doing very well for summer at this part of the ice sheet. Here's now Summit at the annual scale. The warm difference for ERA5, the in situ data are closer for CARRA, and some of the deviation, so they're very close in some years and not so close in others. This may be due to not all of the GCNet data was being assimilated by CARRA. That's something that we need to check. Winter, CARRA, ERA5 is warmer again than in situ and CARRA, so it's looking really quite good for CARRA, but not always. For example, the trend magnitude here, I haven't quite figured this out. It may be that the in situ data, for one, has a warm bias because these are not actively ventilated temperature measurements. That could explain the temperature difference, the inconsistent result. And then a shallower observed trend than in ERA5 or CARRA. These are really quite different results for this central part of Greenland. We should try to understand this better. Again, I suspect some of the error here is actually in the observations. This is a summary table, and so you saw Swiss Camp, you saw Summit, 29, 33 years of data. There are other stations like NASA U here, 12 years of data, or 20 years from Tunu North, and those are on the map. Most of these locations are high on the ice sheet. Swiss Camp was the lowest, but I haven't yet compared with the much lower elevation prom ice sites, and there we'll start to run into terrain bias issues. But in summary, when the box is green, it's a more favorable correlation in general for CARRA, and the bias is lower at the annual scale for CARRA. So the check mark is it's doing better. And at the summer scale, it's actually ERA 5 has a lower bias for this collection of sites. Correlation still higher for CARRA, and the root mean squared difference is lower for CARRA in summer. In winter, CARRA is performing better again with lower bias on average, higher correlation, and lower RMS difference. With the short remaining time, I'll shift to precipitation. And here's the annual total precipitation for CARRA, 31-year average. Maximum here along Iceland, 11 meters water equivalent here in the CARRA data. And so above, around 3 meters, above 3 meters here in Southeast Greenland coast. You have a very dry northeast ice sheet. Oh, apparently, I never knew this. Northern Baffin Bay seems to be quite a dry place at the annual scale. Here's ERA 5. Maximum over Iceland, 3.2 meters or 3.3 meters. Similar regional patterns, and the difference where you get really strong local differences, and then that spillover effect where ERA 5 is wetter inland, and agreement. Well, I've got some more detail in, I think, one more slide. Here you really see again, strong local scales when CARRA can zoom in to 2.5 kilometers. We see a lot of regional detail patterns, and it's delivering, it's concentrating moisture closer to the coasts. I've been comparing not just ERA 5, but some other regional climate models with observations, approximating total precipitation using snow cores data. And the general picture is for all of the regional climate models, including CARRA, is they all have an inland dry difference and a coastward wet difference relative to these data. So this is a map that is attempting to calibrate CARRA to accumulation to account for also drift snow sublimation and other effects, to try to produce the most accurate snowfall accumulation map that we have for Greenland. So this is work in progress, and I think I'll leave it there, and thank you for your attention.